Welcome everybody to the session From Lab to Life about transparent preclinical MRI. My name is Claudia Weidensteiner and I'm from the University Hospital of Basel in Switzerland, and it's my pleasure to moderate this session. We will have 3 speakers today, and afterwards you are welcome to network in Gathertown for the mind matching event. I want to remind you that the session is recorded and broadcasted live. You can post your questions in the Q&A box. All ideas and questions are welcome. Don't be shy. And we will come to your questions after each talk. Our first speaker is Henning Reimann. He's a neuroscientist at the Max Delbrück Center in Berlin. His research focus is fMRI in mice and men, and he's very active in the 3Rs initiative for animal welfare in animal experiments. In his talk, he will present the OpenMinds platform, a platform to share findings about anesthesia protocols and about the effects of anesthesia in rodent fMRI studies. Please, Henning, the stage is yours.
Yeah, many thanks, Claudia, for the introduction and also for the invitation. To me, the invitation came a bit as a surprise since we did not work on OpenMinds for a long time. So we started off with the project 2019. This was on the on the MRathon, and this was a hackathon in Montreal. As a satellite of the ISMRM, and then we stopped working on it on 2021. And this was, on the one hand, due to the pandemic, and on the other hand, I left the field of mouse fMRI and went to human fMRI, and there we mothballed OpenMind and restarted OpenMind in 2023, this year, after I visited a very interesting mouse fMRI workshop in Revereto. And this was one of the reasons I started it again. Another reason was that we wanted to broaden the topic of OpenMind, which was a database usually only for anesthetic effects. And now we want to make it a bit broader, and particularly into the neuroscience and pain research direction. But so here came the invitation, and this was indeed a very interesting surprise because, yeah, it was a nice coincidence. So I start with the general motivation of OpenMind, or the original motivation, and this was that there's a lot of translational research going on between mice and humans, and particularly fMRI is a very interesting tool to directly compare the brain activity, or yes, between humans and mice. And we can do specific other things in each specimen, and the moment we can really compare this, this is a great advantage, obviously. So there's one huge problem, and this is something we still do not have a good solution, or the perfect solution, let's say, and this is that we need to use anesthesia for mouse fMRI. And this leads to a kind of conundrum. So the mouse does not have any interest in participating into an fMRI study, particularly not if it's a pain study, for instance. So we have to give anesthesia, and the question is now, what can we or which protocols can we provide to really sedate the mouse, but have an as much as possible functional brain? And just to give a brief outline how tricky working with anesthesia can be. So we know, for instance, I would start with the effect of anesthesia to the temperature. And mice usually have a wide range of temperature, so they do not have a body temperature of 70 or 37 degrees as we do, but they have a range of about 4 degrees. And if we apply anesthesia, it drops really down to room temperature. So we need to warm the animal. And in the beginning of my PhD, I invested a lot of time to try different mouse cradles and see their warming capacities to really reach a physiological core temperature. And this is not too easy. So we developed one device which makes this possible. And I would like to highlight this particular paper by Christian Baltes. This came, I think, in 2010. And they showed that the head temperature of a physiologically warmed mouse changes so significantly that if you change the temperature of the probe, the head probe, where the mouse scalp resides to, this already changes the bold signal change dramatically, until to a point where you do not see anything anymore if it has the wrong temperature. Another point is, if you give isoflurane, for instance, there was something like a common wisdom that it decreases or it leads to vasodilation. And it was later found out that this is not really the case, but the mice get breathing depressive, and the increased CO2 is the factor that leads to the vasodilation. And because of that, we could not spot the right bold response anymore. And another effect, which I found really interesting as well, is that depending on which anesthesia we use, for instance, a combination of ketamine, xylazine, or isoflurane, we totally see different brain patterns in the brain. And we later found out that this is basically due to an arousal response, which is happening for or which we get for isoflurane and not for the case of ketamine. So all in all, or taking together, the choice of anesthesia is very important, and the effects of anesthesia are very tricky and not at all straightforward. So what we learned in general is that anesthesia have in principle or have certain principles which we can add up, and this is that they work either bottom up or top down. And this means that they work either on the arousal nuclei, which lead to a general cortical arousal or the cortical responsivity, or they work top down by directly inhibiting the cortical neurons. And another effect of anesthesia is that it affects the hemodynamic integrity, and this is directly the neurovascular coupling. So what we see here are some neural populations here, and these here are the vessels. And when we give a stimulus, this is basically the foundation of the bold effect, where we track now brain activity as a surrogate for neural activity, the vascular response. These neurons basically lead to an increase of the diameter of this vessel, and then we have this bold effect. And if we apply anesthesia, this might lead either to baseline vasodilation, and then we have a rather low and sluggish effect, or to vasoconstriction, and then we have a thin and even more decreased bold effect. And so I think this journey in anesthesia started with a talk of Emery Brown, which I once met in a conference on consciousness in Barcelona. And he brought me to the idea that it's basically 3 principles that are always the same. And we, in fact, know way more of anesthesia than I was aware to that time point, and also many of my colleagues who worked in preclinical fMRI. And these are basically GABAergic agonists, then alpha-2 adrenoreceptor agonists, and NMDA antagonists. And they have different different mechanisms. GABA agonists work top-down and bottom-up. Then these alpha-2 adrenoreceptor agonists only bottom-up, and NMDA antagonists only top-down. And based on that, we can also see different cortical signatures, and we have different vasoconstrictions or vasodilations. Not much effect at all. And to that time point, in 2020 already, people used a lot of different drugs to anesthetize the mice. And all those drugs were part of one or either of these large classes. But the reality is way more complex, and every drug on itself has also little side effects that are not predictable by only considering the class. And this is true on the one hand on the neural side, but also on the vasculature. And the complexity gets even increased by the fact that nowadays we started to combine different drugs to get optimal responsivity in the brain. So well, also here taken together, the understanding the effects of the specific anesthesia on the brain function is crucial for basic neuroscience and preclinical imaging. And we need anesthesia for preventing stress and distractions. And we have this paradoxical goal that we need to have a sedated animal with a fully functioning brain. So the refinement of anesthetic protocols is a key for translational research. And this brought us to the point where we saw, okay, the 3R for animal welfare are very much related to that. So if we refine our experimental protocols, this requires to get higher quality regimes, anesthetic regimes. We can reduce the experiments if we have higher quality results, and we can replace the invasive readouts. We can replace invasive readouts at least partially by non-invasive readouts if we preserve homodynamic integrity, or this is definitely a requirement. And there was a very interesting paper in 2019 by Stretch and Dilnagel, and they formulated nicely the 6R principle with adding 3 additional R for scientific value. And they say animal research without scientific value is basically unethical, and I would totally agree with this. And therefore, you could say, okay, register the anesthetic effects and physiological parameters is very important. Then reporting and sharing the findings and the data with the community, and of course, as a goal to establish a robust experimental conditions. And one thing was that I saw that it makes a lot of sense to not only look to the basic neuroscience or preclinical papers, but it's also very interesting if we look to cognitive neuroscience papers and consciousness papers, and on the other hand, to clinical research and practice, and which basically gave me the initiation to that project. And a challenge in all that cases is that valuable information is often buried as side notes in publications, or is unpublished lab law and not available to the community. And this brought us to the idea originally of OpenMinds, and this is an open solution for the community, by the community, at least it was designed as something like that. And the idea was that we, let's say every paper has 5 key points, and then we just extract these key points from the papers, and we put them into a particular data bank. And in the same data bank, we can upload unpublished lab reports. Whatever I find, I can also put as an extract into that data bank. And the data bank was designed based on very strong searching filters, a wiki, and also contextualization. And this is what I'm going through right now. So the database was based on Elasticsearch, and Elasticsearch is something like, from Amazon. I think AliExpress, if I'm not mistaken, uses the same engine, and a lot of larger websites use this for very fast and flexible search. And the idea was, these are two examples for 2 extracts. Let's say miditomidine, this is a special drug, has no dose-dependent effect on the bold response to subcutaneous electrostimulation at 0.5, 0.75, and 1 milliampere, which is an electrical stimulation intensity, in mice for doses of 0.1, 0.3, and 0.71 milligram per kilogram per hour. And then you can click to this little symbol here, this circle in the beginning, and then you see the creator name of that particular extract and the date and how many votes it has. This is something I come to later, and that it's a published article, and here you can see that it's a lab note, which is simply differentiated by the color. Then you can tag these particular extracts. Here we have different filters, for instance, with subcategories or no subcategories. Here, for instance, you have the species. In our case, it would be the mouse. Then we have the anesthetic. Here we would have miditomidine. Then the level, which would be light to moderate, and the physiology. And in this particular paper, they measured hemodynamics and the heart rate. So, and I think also the respiration. So this would be something that we would click on. And also the modality, non-invasive hemodynamics, the scale, which would be a large scale, and the application, which would be here somatosensory electrical stimulation. And these tags, this is now a screenshot from the website. These tags are now by mouse over available, and you can see what you're searching for. And if you search here for your for any extract, you can, or to set on the filters here, you will only get these extracts that are tagged by that filters. And of course, it is also easily possible just typing anything in, and everything else would be then displayed. Every extract comes, of course, with a figure, and this is something which we just downloaded and uploaded from the paper. And here you have an description of the paper, and this is also automatically grabbed from the paper. And you have also, if you click here, you have a direct link to the paper. And this is how you create such an extract. So you can write down what you discovered. You can choose whether it's a published article or lab note. You can put in your figure and put in some comments. Before I continue, these are also very interesting options. You can directly add some extracts that are confirmed by this extract, or in contrast to that extract, or related to that extract in general. And this leads then to the overall context, but I come to that also later. And currently we have the goal to speed this up by having an AI-guided extract creation and also tagging. This is something which is planned. And here I would like to present you a small video walkthrough, and I hope you can hear this, and it would be really great if you could quickly give me a sign if you do so. Here you have a list of extracts, which is still very limited. We just started creating. You can sort them differently, for instance, by publication date. Do you want to see only published articles, or lab notes, or both? On top, you have a specified filter system to tag and find extracts based on the content. Let's go for only findings in mice under ketamine anesthesia. Of course, it's also possible to search by expression. Every extract comes with a figure. You can enlarge it with mouse over. Here's the figure caption. Let's apply another filter. We are now interested in eyes of rain. This is an interesting one. Still a bit preliminary created. Let's see which paper is that from. So let's create another extract from the same paper. You can search the data bank without registration, but to contribute and create extracts, you have to log in with your ORCID account. Now you can see we have here this little edit button. And now we can also create extracts. We want to create an extract on nociception. This function prevents us from creating the same extract twice. No, it's not the same, but it is indeed related to what we want to create. By specifying that our extract is from an article, we can now simply copy and paste the DOI in. Okay, article found. All important info was extracted. The title is a link to the original article. Just open it to search for the respective figure. Let's download the figure and drag and drop it into the input field. Here it is, highly resolved. Here you can input information on the figure. Just copy the caption. Here you can provide source materials like data that is available on open repositories. This is highly encouraged. And here you can set the filter tags according to your study. FMI is non-invasive hemodynamics at large scale. Okay, we created an extract in about 1.5 minutes. Here's the figure and its caption. Here you can see who created the extract. We keep also track on changes. Also, you can vote for extracts if you find them important. You can comment the extract and reply to comments. Here's your related extract. And most importantly, you can create lab notes. Therefore, you have manual input fields.
You may also pick a representation of the findings. We highly encourage to provide access to the original data. And that's it. That's OpenMinds so far. It is our first beta release, and I'm really delighted to share it with you.
All right, okay, this was the video walkthrough. And here's a little summary, or the anatomy. So if you want to create an extract, you go through your ORCID account, then you can tag it. If you just search for an extract, you can do it open without any registration or anything. Here on this side, you have the content and the search database with the figure and the specification. And here you have dynamic content, which are the comments. I come also to that in a minute. And here we have the context. And I already showed what it is about the related and the confirmed, and in contrast to, and this is also a function which I personally found very important, and this is something we also want to improve a little bit. So to quickly highlight the wiki again, okay, this is the comment section, and now I can just write something which I believe is important. Medetomidine is a one-dimensional drug. Okay, I could specify this a bit further, and then I could provide a link to the source or the extract which shows this. And thereby we get an overall connected database. And here another comment, which is a comment to that comment, for instance. The context works like this on the creation side. This is what I already showed. You can basically type in whether or how many are related, confirmed by, in contrast to. On the extract search side, you can just click on this here on related, and then you have such a menu, and then you see, okay, related to 8, confirmed by 12, in contrast to 6. And then we work at the moment also on a visualization of these, and this makes it easier. This is, of course, with mouse hover, if we're interested in. You can also just display the names here of the first author, and then you directly see what it is and how these extracts are connected. And also this visualization, I think, is very helpful. And the next step, we also want to introduce OpenMind maps, and this makes it even easier with just dragging and dropping extracts in. And here, for instance, I have just a very bare minimum option bar, and then I can draw a particular background, and then I can just drag and drop extracts in. And I could here, for instance, provide the table that I showed you in the beginning. And here I put particular extracts in that show me which effects particular drugs have on particular networks. This would be one idea to work with this. And of course, you can also work on this in teams. That's very important. And here, this is also a nice feature which I'm looking forward to use myself. This is an on-the-fly drag and drop referencing, and this is also something we can do in collaboration with other people. So basically, here we can search for the extracts, and then we can write a text, a paper, whatever, and then we can just drag and drop this in. And by clicking on that, we are hovering over, we have directly then here the extract again. And of course, as I said, you can do this in a team, and therefore it makes it very straightforward to work with that tool, for instance, in the lab, but also over larger collaborations. Yeah, and that's basically it. So the idea is at the moment to expand this towards broader topics. We started with anesthesia, but we want to have this as a general tool for scientific communication and collaboration. And yes, that's basically it. Thanks for the attention.